Okay, good afternoon, everybody. So, hypothesis testing on differences in the means of two normal populations. So, in general, we want, yep.
Good question. Homework got assigned today.
Yes.
During spring break. Is that right?
Yeah, it's
due on Friday.
is
It's due on the Wednesday.
The Wednesday.
Is it due on the Wednesday?
no Wednesday after spring break.
Oh.
No. Right now
No.
it's
23rd?
Yeah.
Oh no, it should be 30th. So yeah, we'll fix that. Thank you.
Awesome.
Yeah. So it's Wednesday after spring break. So it was just a mistake. Yeah, thanks for letting me know. So in general, what we want to test is whether the difference between means of two normal populations is delta 0 or not. And the most common delta 0 is what? 0. Whether they are equal or they are not equal. And we know that basically it follows a normal distribution, x bar minus y bar, and we can define this z0 test statistic. And again, everything else is as usual. If the absolute value is greater than z alpha over 2 for the two-sided, then we reject h null. For one-sided, these are the critical regions, as you can see. So again, the more general case is mu1 minus mu2 is some number, versus it's not that number or greater or less than. We can do basically hypothesis testing based on confidence interval, how we construct the confidence interval for mu1 minus mu2, and if the delta 0 value belongs to this confidence interval, we cannot reject, otherwise we reject h null. That's simple. And this is for like a summary how to calculate also p-values. You can see it here. It's similar to one population. The only difference is the way that you calculate your test statistic. That's it. Okay? Any question? So let's see one example. A product developer is interested in reducing the drying time of a prime paint. They have two basically formulations. So two formulations means what? Two populations. The first one is a standard one. The second one has some drying ingredient that should expedite drying time, or I'm sorry, should expedite the drying process. From experience, it is known that a standard deviation of drying time is 8 minutes. Okay? As I said, from experience, from historical data, whenever you hear these words, it means this is sigma squared, not S. Okay? And 10 specimens are painted with formulation 1, and another 10 specimens are painted with formulation 2, which means N1 and N2 are equal. Both of them are 10. And there is also one more sentence, one more important sentence. This inherent variability should be unaffected by the addition of the new ingredient. So what does it mean? It means sigma 1 squared and sigma 2 squared, both of them are the same. And actually sigma 1, because it says a standard deviation, are the same, and it's equal to 8. Okay? And N1 is equal to N2 is equal to 10. We calculate x bar 1. It's 121. X bar 2 is 112. And we want to see basically what conclusions can the product developer draw about the effectiveness of new ingredients. So we want to see if it is effective or not. So what does it mean when we say effectiveness? So if we want to say it's effective, the ingredient is effective in terms of drying time. So let's say mu1 is without ingredient, mu2 is with ingredient. So this should be 0 for h null. So which means there is no difference between these two, and H null says it's not effective. How about H alternative? Should be less than, greater than, or unequal. So mu1 minus mu2 should be greater than 0. In this case, I can say it's effective because the time is smaller, the drawing time is smaller for the second population with ingredient. Okay? Make sense? So what we need to do, we need to calculate Z0, which is basically x bar 1 minus x bar 2 minus delta 0 divided by standard error. In this case is 121, 112 minus 0, because delta 0 is 0, and 8 squared divided by 10, 8 squared divided by 10. This value is 2.52. By the way, alpha is 0.05. Therefore, your rejection region for this case is Z0 greater than Z of alpha. This is the rejection region. So this is rejection region. So what is your Z0? 2.52. Z of alpha is 1.645. So 2.52 is greater than 1.645. Therefore, we reject H null. Therefore, it is effective. Okay? Any questions?
The specimens are painted in random order?
Yes. Yes. So basically, when you say like random sampling, that's part of it. Why? Because let's say if it is not in random order, okay, then there could be some non-random variable which could affect your basically painting. Okay, for example, over time, temperature changes. If it is not random, then you are including the effect of temperature as a kind of like a bias factor. Okay, this is very important when you have more than 2 levels, which is the topic of ANOVA. Okay, any questions? Is it clear? So as you can see, if you learn hypothesis testing for one population, 2 population is very similar, just changing or generalizing the test statistic. Okay, how about n? How we can calculate n in this case? And as you can see, Z alpha over 2 and Z beta is very similar to what we had in one population. Instead of sigma, we have sigma 1 squared and sigma 2 squared. By the way, in this example, we assume n1 is equal to n2 is equal to n. Okay, that's the main assumption. Okay, but when you get n, it means your n1 and n2 should be at least this number, at least. Okay, if you go above that, then you get more power. So it's not necessary for the case that basically n1 and n2 are equal. Okay, what is delta minus delta 0? So this is basically when you say mu1 minus mu2 is not delta 0, so it is some other number, we call it delta. Okay? So the difference between, if H null is not true, this is H alternative, so the difference between H alternative and H null. Okay? That's the difference between H alternative and H1. And previously we had what? Remember, for one population we had mu1 minus mu0. You remember? And we call this delta. And this is for one-sided hypothesis testing. Any questions? I think there is one example, yes. So to illustrate the use of these sample size equation, we are considering same example. We say if the true difference, we know that H null is not true, okay? If the true difference between drawing times, so we know that the drawing time is not 0. If the true difference between drawing time is what? It says is 10 minutes. So delta is 10 minutes. Okay? And we know that delta 0 is 0 because this is under null hypothesis. So what would be n if we want to gain 90% power? Okay? So power is 90%, which means beta is 10%. Therefore, z of beta is z of 0.1. Alpha is 0.05. Z of alpha, this is one-sided, is 1.645. And this guy is 1.28. So if I go back, this is the equation we are going to use. Which one, the first one or second one? Second one, because it's one-sided. Because this is this example, actually. It's one-sided. 1.28 plus 1.645 squared. Sigma 1 squared plus sigma 2 squared divided by delta, which is 10 minus 0 squared. If you do this calculation, you get 11. So basically, your N1 and N2 should be 11. I mean, greater than 11. At least 11. Okay? Any questions? Okay. So what if we don't know the variance? Remember, there were two scenarios. One, we don't know the variance, but we have this main important assumption that sigma 1 squared and sigma 2 squared are equal. That's case 1. So in this case, we can estimate that sigma, common sigma, using pooled estimator, which is this guy. And then we know that our test statistic changes from Z0 to T0. Okay? So we have T distribution. What is the degrees of freedom? N1 plus N2 minus 2 degrees of freedom. And here is basically the rejection region. You calculate this T0 for inequality. If it is greater than this critical value, you reject it. Or you can compare your delta 0 with the confidence interval, or you can use basically p-value method. Again, that capital T is what? Is CDF. Okay? Any question? So two population variances are unknown. We need to estimate it using pooled variance. But the main assumption is sigma 1 squared and sigma 2 squared are basically are equal. Does anybody know how we can validate this assumption? No idea? So later on, you are going to learn about comparing two variances of two populations, whether they are equal or not, using hypothesis testing. Okay? that could be used for validating this assumption. So you haven't learned yet. But yeah, using hypothesis testing for comparing the variances of two normal populations, that can be used for validating this one. Anyways, so we have two catalysts that are being analyzed to determine how they affect the mean yield of a chemical process. So two catalysts represent two different populations. Catalyst 1 is currently in use. Catalyst 2 is acceptable. And what we want to do is basically, we know that Catalyst 2 is cheaper, okay? And we want to see if their performance is equal or not. If they are equal, we are going to go with what? With a cheaper one, okay? So we collected 8 observations from each catalyst. So we basically ran the experiment or the process 8 times using catalyst 1 and 8 times using catalyst 2. Okay? We get the numbers, and the numbers, I think, is process yield. And we want to see if they are equal or not. Let me see if I have numbers here. Yes. I think alpha is 0.05, so I keep it as is. But our H alternative is different here. What is H alternative? Mu1 minus mu2 is not 0. So there's a difference between their performances. Okay? So it's two-sided. Therefore, I need to look for Z alpha over 2, which is 1.96. Okay? So X bar 1 is 92.255. X bar 2 is 92.733. The sample variance for the first population or first catalyst is 2.399, and for the second one is 2.98. So what is the first step? We need to find this guy, pooled variance. Okay? Pooled variance is (2.39) plus 8 minus 1, 2.98, divided by 8 plus 8 minus 2. So I'm using this equation for pooled variance. And 1 and N2 are the same, equal to 8, because I have 8 observations, as you can see. So this number is 7.3. Therefore, the standard deviation is this guy, which is 2.7. So what is the next step? Find T0. So X bar 1 minus X bar 2 minus delta 0 divided by SP 1 and 1, 1 and 2. In this case is 92.255 minus 90.733 divided by 2.70. Actually, I made one mistake here. So here it's the T distribution. So we don't care about Z. We need to find T of 0.025, and the degrees of freedom is what? 8 minus 2, which is 14. From table, this guy is 2.145. Let me double check. Yes. So the absolute value of T0 is 0.35, T alpha over 2, and 14 degrees of freedom is 2.145. This is less than. So what is the conclusion? Do not reject H null, so you can use catalyst 2. There is no evidence for saying that catalyst 1 is better, or there is a difference between these two, therefore we can use catalyst 2. Okay. Question?
Standard deviation is 2.39 and 2.98.
These two are, let me see. You are right. These are standard deviations. So I need just to, the answer is correct because I'm reading this part, but this should be a squared. Yeah, thank you. Thank you. Any other questions? Okay. So, what if the variances are not equal? In this case, if you remember, the test statistic under H null approximately follows a t-distribution with this weird degrees of freedom. Okay? But everything else is the same. What you do, just replace degrees of freedom with this new. Instead of n1 plus n2 minus 2, you have this new degrees of freedom. Everything else is the same. Okay, let's go over same example when the variances are not equal. Okay, I don't have the answer, but let's do the math. Actually, we don't. I'm sorry?
Is it in the book, if you wanted to answer?
No, it's not in the book because I have the book solutions. But maybe somebody can help me if you have calculator. Okay, so what we want to do, our actually t statistic is also a little bit different. Instead of SP, we have S1 squared divided by N1 and S2 squared divided by N2. Since the variances are not equal, we cannot combine basically the sample variances. Okay? So we need to do it separately. So let's just start with x bar 1 minus x bar 2, which is 92.255 minus 92.733 minus 0, and S1 squared, which is 2.39 squared divided by 8, and 2.9 squared divided by 8. If somebody can tell me what this number is. Do you have it? Not yet? Okay. So you also need to calculate degrees of freedom. Degrees of freedom is 2.39 squared divided by 8 plus 2.98 squared divided by 8, and the same thing the whole thing squared divided by 8. Again, the whole thing is squared divided by 8 minus 1. Okay, so then what you need to do you need to compare this T0 with T of 0.05 and this new degrees of freedom. Okay? If it is greater than this, then we reject H null. Okay? So you can do the math at home. It's not going to be very difficult. You have number?
Degrees of freedom, and if all my calculating was correct, just punching the numbers in, it was 14.
14?
Yeah.
Okay. Basically, it's very similar to the previous one. And why is that? Because the variances are actually similar. Okay? So in this case, variances are similar. That's why these two should be very, very similar. So it's almost 14, and then so it's basically you're comparing with this guy, which is
Actual samples.
you can actually go both ways. You can round up once and round down and see if there is any difference between conclusions or not. Yeah, because this is approximate. It's not a basically exact test procedure, which is 2.306. Okay. This one? Oh. 13.4. Let's call it 14. They are very, very similar. Okay. Any questions? Is that clear? Okay. Now, job number? That's okay. They can calculate at home. Don't worry. Okay. So paired t-test. Sometimes you have two populations, but these two populations are not independent, the samples of these two populations. So basically, you remember, this is very important assumptions in all basic hypothesis testing. We have two independent random samples. So random sample, within each sample should be independent, between samples should be also independent. In some cases, we have dependent samples, and it's because of the nature of the problem. For example, you are collecting the data in pair. So sample 1, x1 and x2, they are being collected in pair. One example is analyzing the difference between hardness reading of each specimen. So you have one specimen, you do reading using the first instrument and use the same part and do another reading using the second instrument. So you can see you are using the same part for both of them. So this creates dependency. Does it make sense? Then second part. Let's say this is the second part. Use a specimen 1 to measure the hardness, and then use a specimen 2. Use instrument 1 to measure hardness. Use instrument 2 to measure hardness, using the same basically a specimen. That creates dependency. Another example is the case that we call before and after test. For example, you want to see the efficacy of a drug or a diet program. So what you do, you measure the weight of one person before basically a diet program, and you measure the weight after the diet program. So you are measuring the weight of one person twice, before and after. Okay? So you're using the same person. Therefore, your sample from before and your sample from after are dependent. Why? Because this is one person. This is another person. This is another person. And so on and so forth. Okay? Is it clear the dependency between these two? So what would be the solution? Very easy. If you subtract, then you get rid of dependency. Okay? That's how it works. So instead of working with 2, you subtract them. You find D, which is the difference between each pair. Then it reduces to what? To one population test. Because you have only one. Does it make sense? And what you do, you test whether the average of differences is 0 or not 0. Okay? Or in this case, in general case, it's delta 0 or it's not delta 0. Okay? So it's the t-test. Why? Because I don't know the population variance of the difference. Okay? And so the degrees of freedom is very interesting. If I wanted to use 2 population tests, what would be the degrees of freedom? N plus N minus 2. However, when I subtract them, degrees of freedom is what? N minus 1, because I'm making it one population. Does it make sense? Okay. And the rest is very easy. It's just one, basically, population t-test. Question?
Is this measuring the dependency of the samples?
No, it's removing the dependency of samples by subtracting and making independent. Okay? So, for example, and that makes sense. So, weight, okay, it's depends on a person plus the effect of your diet program. Okay? So before diet program, your weight is what? Only mu. Okay? So what you do when you subtract them before and after, this is the dependency. You are subtracting mu, and what you have is only the effect of diet program. So you are removing the effect of subject. Okay? So again, weight of subject I is, let's say, mu I plus the effect of the diet program. This is for after. For before is this. And as you can see, both these two, let's call it W1, W2. These two are dependent. Why? Because both of them have mu I. When you subtract them, so what happens? You only have tau I. So this is the dependency cause. So you are removing that dependency cause. Make sense?
Variable, then they
That's how
become
it's
independent samples, right?
What is it?
If tau becomes a random variable, then the 2 samples become independent. Is that right?
Then you don't have any 2 samples, just 1 sample. Because you are subtracting the first one from the second one, so you have 1 column of numbers.
Right, but I'm just saying that if tau was a random variable,
It's a random variable, actually. That's true.
then
Tau is a random variable. But that randomness
So you're just trying-
is
okay.
between subjects.
Okay.
That randomness is between subjects, not between before and after. Because we know that the subjects are independent. So we know rows are independent. Columns are dependent. By subtracting them, you get 1 column, but still rows are independent. Does it make sense? Okay, good. Question?
From pairwise to more cases, like you, instead of doing it just before, after, you do it several times on a time scale.
Oh, no. That one is, I know what you're saying. So one subject, for example, you are doing experiments 7 times. You cannot use pairwise. There is something called longitudinal data analysis or something called two-way ANOVA. We will learn that actually. Two-way ANOVA at the end of it. You have multiple machines, yes. This is called one-way ANOVA. This is two-way ANOVA. The extension, to generalization of that to the higher populations and higher, basically, dependency levels. It's called two-way ANOVA. The other one is called one-way ANOVA. Yeah, we will learn that, actually. Any other questions? Let me ask you a question. So you can see this is much simpler, right, compared to this guy in terms of calculations. Why don't we use always this compared to two population t-tests, this guy and this guy? What is the reason? Why do we need to use that type of test? Yeah.
You paint the same sample, be the same?
Yes, exactly. Some cases, you can use one sample. But the same, I'm not talking about the logic behind that, but I'm just saying in terms of calculations. If you have two populations, you can subtract them. Right? So you subtract them again, because this is normal population. This is normal. If you subtract them, again, it's going to be normal. So mathematically, you can do that. That's fine, because there are two numbers. No, actually, both of them you're talking about like when we subtract. So this is population 1, this is population 2. So we are subtracting these two. It doesn't really matter. So one thing is very very simple. Here we have the assumption of n should be equal. All right? So we are talking about pairwise. Okay? So n1 and n2 is equal. Previously, we didn't have this assumption. Okay? So n1 and n2 could be different. That's one reason. By the way, if you have unequal, basically n here, you need to remove one of them. For example, if you have 10 observations here, 12 here, you need to remove 2 of them, okay, to make them pair. But there is another reason, more important. Anybody? Yep.
The test you use assumes equal variances?
No, you can use for unequal variances as well. So actually, it's a good way of getting rid of that condition, because when you're subtracting them, there is no two variances, you know.
Is it the randomness in which they're painted? Like they couldn't line up?
But yeah, that's basically related to what he said, but
Physical?
yeah, just mathematically we can do that because there are two numbers.
Do you have the actual data in this case? The other one might only have.
No, actually, in both of them we have actual data. We do actual experiment. Okay, nobody can. I won. So what happens here, if you look at the degrees of freedom. So degrees of freedom for this guy over there, when you have two independent, the degrees of freedom is n1 plus n2 minus 2. Okay? So your effective sample size is n1 plus n2 minus 2. In case that n's are equal, this would be 2n minus 2. What is the effective sample size here? Is n or n minus 1 is the degrees of freedom. Okay? So we know that when we have more sample size, we have more power. So this test is more powerful. So that's why when you can do this test, you go with this guy rather than this guy. By subtracting them and losing some, basically, sample size, you are losing some power. So you don't do this type of test unless you have to do, which is basically the dependency. That's the main reason. Make sense? Okay, good. So one example. So we are comparing several methods for measuring shear strength for a steel plate and data for two of these methods. I don't know what these procedures are. Anyone from mechanical engineering familiar with these two? But anyways, so there are two different procedures. We have non-specimen. So the specimens are here. We measure using the first method. The same specimen we measure with the second method. Therefore, they are dependent. So how many of them do we have? Like 9. And this is the measure for the first method, the second method, and we want to see if these two methods are equal on average. So basically, what we want to test is there any difference between these two or not? Okay? Since they are dependent, why? Because for each method, I'm using the same specimen. We need to use pair T. Okay? And DI is XI minus YI. So we calculate the differences. Let's see, where is it? It should be somewhere here, yes. For example, for the first one, second one, third one, method 1 and method 2, this is 1.186, 1.061. Your D is the difference, 119. So what we do, we calculate D bar. D bar is 0.2736. Okay? And we need to find T0, which is D bar minus 0 divided by an SD. Standard deviation of these numbers, again, is 1.1356. So 0.1356 divided by square root of 9. That gives me 6.05. Okay? So I need to compare it with T of because alpha is 0.05. It's not there, but we assume it's 0.05. T 0.025. What is the degrees of freedom here? 9 minus 1, which is 8. With 8 degrees of freedom, this guy is 2.306. So we compare this one and this guy. So your T0, the absolute value, is greater than 2.3. Which is 6.05 greater than 2.306. Therefore, reject H now, and these two methods are not equivalent. Okay? Any questions? Is it clear? Okay, good. We have 5 minutes. I have your exam graded finally. And so I will do some analysis. I usually curve the grades. So these are basically raw grades. On Monday, I'll give you some statistical, basically, report, and then I show you how to grade it, how to curve it, So it's a statistics class.